Lesson 3.4, Product and Quotient Rules. Recalling from our past, if we have this function g of t, which is a product, I can easily multiply the two expressions together, get a single function in terms of term 1 and term 2 to be able to use the power rule and get g prime of t. However, not all functions you will be able to combine and multiply to create a simpler expression. So we have something called the product rule. And the product rule basically states that you take the derivative of one function, multiply it by the other as is, and then they flip-flop roles. As a little mnemonic device, you can remember first derivative second plus second derivative first, but I think it's easy enough to just remember take the derivative of one factor, keep the other one the same, and then flip-flop. So I take my g prime of t, and I am going to take the derivative of this first, negative 4t to the negative fifth. I keep the second one as is, plus, now the first one stays the same, and the second one gets derived. So the derivative with respect to t, that's working like x, so that goes to a 1, plus b in this case is a constant multiplier because t is the variable who's changing. So I have 3bt squared. Distributing through, I have negative 4t to the negative 4 minus 4bt to the negative 2 plus t to the negative 4 plus 3bt to the negative 2. Combining my like terms, I get negative 3t to the negative 4. Next like terms, I combine, I get minus bt to the negative 2, which is an exact match to what we discovered up here in the beginning. So the product rule is valid maneuvering to find derivatives of products. The next is going to be the quotient rule. So we'll start with an old example. This problem is really 7a to the negative 4/3 using our algebra skills. If I take and just use a simple power rule, the negative 4/3 comes in front, multiplies, we have negative 28/3 a to the negative 7/3. The quotient rule. The quotient rule is this kind of complicated expression, and there's a little mnemonic device to help you remember this complicated expression. And it goes something like this. It's much better in person. Low d high minus high d low over low or low squared. Now how does that mnemonic device work? Low stands for the lower function. The lower function is g. D high means the derivative of the higher function. Here's the higher function, so there's its derivative. Minus high. High is the higher function. D low, you're taking the derivative of this lower function. And I know you're all laughing and chuckling at me, but it would be even laughing more if we were in person. And then over low squared, well, it's the bottom function being squared. Because order matters in subtraction as opposed to products, that's why you have to remember to start low. Start with the low one. So it goes low d high minus high d low over low squared. To apply it here, I'm going to say m prime of a equals, and I'm kind of looking ahead, and I'm going to change this quotient so that it's 7 over, and then I'm going to make it a to the 4/3. So that way I can use my power rule and not have to use a product rule within a quotient rule. Anytime you can simplify, it's a good thing. All right, I start low. The low function is a to the 4/3. D high, derivative of the upper function, the derivative of the constant goes to 0. minus high, there it is, the higher function, d low, 4/3 a to the 1/3 power. All over the low or low squared. Simplifying, we get negative 28 thirds, a to the 1/3 being divided by a to the 8/3. Simplifying again, negative 28 thirds, a, 1/3 take away 8/3 is negative 7/3. I get the same matching answer to what I have up above. So those are two rules, product and quotient. Applying them here. C of x could easily be multiplied, but with ease, people tend to make some kind of silly arithmetic and algebraic mistakes, so I'm going to stick with the product rule. I'm deriving with respect to x. I'm going to take the derivative of my first, e to the x, easiest derivative, it repeats itself, plus e to the first. This is a constant. Its derivative is 0. Times the next one as is, plus, and now they flip-flop roles. First stays as is, and then derivative of the second, I have a constant, minus e to the x, it's itself, so I keep it as e to the x. For simplifying purposes, they're both being multiplied by an e to the x. So I could say e to the x times whoever's left. I have e to the third minus e to the x, and then I'm going to put the negative sign with both of these terms, minus e to the x minus e. Simplifying again, I have e to the x times e to the third is a constant. I have two like terms, then minus the constant of e. And there's my answer. For function j, I'm deriving with respect to k. So j prime of k equals, and then we're going to say low, because we start with the lower function, k squared plus 3k d high. Derivative of the upper function is 4 minus the higher function, 4k, derivative of the lower, 2k plus 3, all over low squared, or the denominator squared. General rule of thumb, oops, that's j prime, when simplifying for these, it is not worth expanding out the denominator, because one of two things will happen. First being something might cancel with one of those factors once I simplify in the numerator. And the second is if I'm evaluating the derivative at a point, it is much easier to evaluate it in factored form. So we're just simplifying the numerator. 4k squared plus 12k minus 8k squared minus 12k. All over the k squared plus 3k squared. J prime of k is now going to equal 4 take away 8, negative 4k squared. These two cancel, left with k squared plus 3k squared as my derivative of j. We are given some information about function f and g at the value of 3. We want to find the derivative at this value of 3. In general, I strongly recommend you find the derivative rules first in terms of x and then sub in. So the derivative of function f minus g of x. This is a difference rule with a constant multiplier. F goes to f prime of x minus the constant is just carried along times g prime of x. Then I go for evaluating it at 3. F prime at 3 is 5 minus 8 times g prime at 3 is 6. I have 5 minus 48. I get a negative 43. F of x here is a product and a difference rule. I'm going to start with f prime of x. Always do the general derivative first. Derivative of 4x squared is 8x. Second one's staying. Plus, flipping it around, 4x squared stays. F prime of x is now derivative. Minus derivative of x is 1. F's derivative at 3. I have 8 times 3, which is 24. F at 3 is negative 3. Plus 4 times 9 is 36. F prime is 5 minus 1. And then you can take and just calculate those all out. And we get 107. My next one is a product with differences inside. F prime of x equals, let's go for the derivative, f prime of x minus 7 times, as is, plus, flipping it around, f of x minus 7x stays, and the derivative constant goes to 0. Keep the negative sign, negative g prime of x. As a general rule of thumb, when you're evaluating, I don't simplify first because I'm going to be plugging in and it's easier to work with the factored form. F prime of 3 is 5, take away 7. Then I have 8, take away g of 3, which is negative 4, plus f at 3 is negative 3, and then minus 21, times the opposite of the g prime, so that's negative 6. We have negative 2 times positive 12, plus negative 24 times negative 6, and then we're going to total that up, so we have a negative 24, and it'll be plus, we end up with 120 for the final answer. Oops, sorry about that. The last one, number 12, for this page rather, f prime, again of x. I'm going to keep my low as is. Oops, that minus sign is getting lost. Times the derivative of the high, low d high, minus, and when you all come to class, I'm going to say low d high, will be animated together, minus the high function times the derivative of the low. The 2 is a constant, it goes to 0, keep the minus because it's a difference, and then it's f prime of x in that spot, over 2 minus f of x squared. At 3, we're going to have 2 take away negative 3, so that's a 5 times the 5 minus 15 plus 1 is 16 times the opposite of my f prime, so that's a negative 5, and then we have that over the 5 squared, which is 25. So then I end up with 25 plus 80 being divided by 25, 105 over 25. Don't need to simplify unless you're looking for a multiple choice answer to line up. These rules can be applied through both tables and graphs. You just have to go to the corresponding either table or graph to find your information. In 13, function h is a quotient. If I want to evaluate it at 4, I'm going to say h prime, okay, in general, not necessarily at 4, is going to be low, d high, minus high, d low, over the low function being squared. H's derivative at 4 then will be, we have f at 4, which is lining up, hopefully my eyes are working this morning, at 3, times g's derivative at 4. So here is 4. G's derivative at 4, we have a slope of -1, minus g at 4, that's at a height of 1, times f's slope at 4. Oops, my eyes are off here. F slope at 4, which is here, which is a slope of 2. Let me just double check. Yes. Over the value of f at 4. F at 4 is 3, so that's 3 squared. -3 minus 2 gives me -5 over 9. H prime is equal to function f first. It goes straight to its derivative. Difference rule, constant multiplier, so the constant gets carried along with g's derivative. H prime at -4 is going to be f's slope at -4. So I go to the graph of f, they're intersecting here, that's okay. I want the slope at -4, and it's looking like -2 minus 6 times g's slope here at -4, so make sure I'm on the right curve. Looks like down 1 over 3, so we have -1/3 for the slope there. Combining, we have -2 plus 2, so we end up with a derivative value of 0. H is now a product. Its derivative is going to be f prime times g plus, flip the roles, f stays, g goes to derivative. H prime at -7 is going to equal slope of f at -7 is looking like that -2 still. So I have -2 times the value of g at -7, which I believe is 4, plus f at -7 is up here, and I believe that one is 9. My 10 is a little shifted on the graph there, times g prime at -7, which is -1/3. So I'm combining my -8 minus 3 to get -11 for h's slope at -7.